So, so before we have learned how to do the smoothing splines on the discrete functional data, how to transfer discrete observations of functional data to a continuous curves, right? So we learned how to define the roughness penalty to control the roughness of the curves, okay? And also we have learned one important topics or tools in functional data called functional principal component analysis, and we have learned that FPCA can be used very effectively for the dimension reduction and also to prediction on the new observed functional data. So far we only focus on one functional covariate, one functional variables, or we have worked on multiple. We have worked on the multivariate functional variables when we work on the multivariate FPCA, but we only consider the correlation, right? Yes. So we know in statistics there's a very powerful regression models which can relate covariates predictors to the response. So in functional data, actually there's also similar versions on this regression framework. So here, in this slides, it shows the simple multiple linear regression model. So we have a response yi, and we have some covariates xij, right? So we want to relate the yi to the covariates xij. So here we're using these linear models, and we have these two coefficients, alpha and beta j here. So in our functional data, so we are dealing with curve now. So therefore, there are three possibilities. So the first possibility is that in our covariates, so maybe there will be functions there. In other words, there will be some x, which is the function of t. Okay, so this is called and the response is still a scalar. So this is called a function on scalar regression model, also called. Okay, so this is one version. The other version is that the response is a function. So yi is a function of t, and the covariance xi is a scalar. So this is also called a function on scalar regression model. So the last scenario will be both the response yi and the covariance xi are function of time. So in this case, we will call a function on function regression. Okay. So in functional data, we have these three versions of functional linear regression model, and so we will learn these three types of functional linear regression models in turn. Okay, so now let's work on the first examples. So here, this one again is to show the delay temperature, average temperature of 35 Canadian cities. Okay, so we have used this data a lot, and so now we introduce a response, which is the annual precipitations. Okay, so the annual precipitations will just a scalar response. Okay, so we want to relate the annual precipitation amount to the temperature curves. So this will be a scalar on function regression problems. So here, basically we have observed yi, the annual precipitations. So I is the index for the 35 Canadian cities, and xi of t will be the average temperature for the 35 Canadian cities, right? So what we can do here is that we can treat the temperature curve at each time point as one covariate, right? So basically here we have 335 days. Then we will have 335 covariates. So J will be the index for the time. So then we can doing the regression of yi on this xitj, right? So there's no problem. So the potential problem is that first we need to decide how dense these time points should be, right? So we have 335 days with observations, but after we smooth the temperature curves, we know that we can evaluate the temperature curve at any dense grid points, right? So therefore, it can be very different if you choose different grid of time points. So this is the first problem. The second problem is that so here this beta j, this coefficient slope represents the effect of the temperature on dj on the annual precipitation, right? Okay, so you can think about, because of the temperature, it kind of have the smooth change, right? So therefore, all these beta j's should also have the effect. We also should have a pretty smooth change. All the beta j should be similar in the neighbor time points, right? Should not have a quick change. So therefore, when we do the estimation on the beta j's, we should have somehow control that the beta j should not have a big jump in some neighbor time points, right? So this is kind of a big thing we need to control, right? Okay. To control this actually is not that easy, right? But we can, if we treat the xi of t as a function, then actually it will become pretty natural or straightforward to solve the above two problems. Okay, so in other words, here we treat xi of t as one whole curve. Okay, so we related this whole curve xit to the scalar yi. Okay, so now we have this on the right side is this curve xi of t, right? And on the left side is the scalar response of yi, the annual precipitations. So in order to relate to the function to this scalar, we can bring an integral, right? So then we put an integral here, and then we put a coefficient. The coefficient now also change to the function of time t, okay? So then we will have the integral of beta t times xit dt, okay? So then this integral will become a scalar, right? So now we can do the regression of these functions on the scalar response. And here, this beta t, the slope function, represents the effect of xit on the yi, right? And if you think about, if we can control the smoothness of this beta t, we will control the effect of temperature on the precipitations. It also has a smooth change. Okay, so this is the functional. This is the functional linear models we use. This is also called a scalar function regression models. So here, alpha is the intercept, basically epsilon I is the measurement errors. Okay, so here to simplify our problem, we assume epsilon I has mean zero and variance sigma square. Okay, and then we can estimate these two parameters alpha and beta t by the mean square errors, right? So we minimize the summation of square of this yi minus alpha minus integral beta t xit dt, right? Okay. Yes. Any questions? Is this clear? Okay. So so there's a potential problem for this functional linear regression model. The reason is that here this beta of t actually is a function of time. So we know a function, a continuous function, actually is the infinite dimension, right? So in other words, if there's no control on the beta t, then we should be able, then the number of parameters will be larger than the number of observations. Okay, so therefore, we will have zero residual. We will overfit the data. Therefore, we must have some control on the number of on the smoothness of the beta of t. So the idea is similar as before. When we want to control the smoothness of beta t, we just add a reference penalty on the beta t, right? So now we have the penalized sum square errors, and so we add a reference penalty on the sum square errors, and the lambda is the smoothing parameter. L is the differential operator. So we will estimate the beta of t by minimize these penalized sum square errors. So to represent beta of t, we use a basis expansion. So beta of t will be equal to the summation of ci times phi I of t. So phi I of t is the basic functions, ci is the coefficients. After we doing these representations, we can plug in the formula of beta t on these penalized sum square errors. So because beta of t is equal to the linear combination of basic functions, so if we write down phi of t as the vector of the basic functions, then the beta t will be equal to phi of t transpose times c, right? So then, because this basic coefficient c is not a function of time, so we can take this c outside the integral, right? And then in the integral will become integral of the basic function phi of t times xi of t dt. So we assume that xi of t is known, right? The basic function are decided by us. So we are also able to evaluate these basic functions phi of t. So therefore, we should be able to evaluate this integral numerically, right? Okay. So if we treat this integral, so this is should be a vector, right? So if we're using j basic functions to represent beta of t, so then this will be a j 1 by j vector, right? And then we denote this as a vector xi, then this will become regression, the regular regression problem. So yi will equal to alpha plus xi transpose times c plus epsilon I. Okay, so then if we plug, we define the z as as the covariate design matrix with the first rows as 1, and the rest rows will be this xi, right? And then we can write down this as the matrix form y equal to z times alpha c plus epsilon. So suppose here we have j basic functions to represent beta of t, then alpha c will be j plus 1 length j plus 1 vector, column vector, right? And this z will be n times j plus 1 matrix. Okay, so then this will become a regular linear regression problem in matrix form. Okay, and so then we can plug in these estimation, these representations to our penalized sum squares with this penalty. Recall that this penalty can also written as a quadratic form on the basic coefficient c, right? So therefore, we should be able to express these coefficients, basic coefficients, in this formula. Okay, so this kind of a rigid regression looks like a rigid regression formula. Okay, so this R is the penalty matrix, and only depend on the roughly the penalty you use. Okay, so this is the estimation. So after we get the estimation for the basic coefficients c hat, then we will know the basic the coefficient function beta of t, right? So then we can get the fitted value y hat equal to alpha. This should be alpha here. Alpha plus the integral of beta hat of t xi of t dt. Okay. So and after we plug in the formula here, we should be able to write this also as a matrix S times the original data y. So in other words, here y hat equal to S times y. Okay, so so this S will be kind of the hat matrix for our linear regression model, right? So the reason we want to write down this y hat equal to sy is that what's the reason we have this s here? Can anyone tell me? Alex, what this s will tell us?
So like a projection matrix?
Projection matrix, okay. So how do we use this projection matrix? Okay, anybody have ideas? What's the useness for this projection matrix S? Can you know?
You can calculate the trees of S can give us information about the degree of freedom of the model.
Right.
So when we want to use model selection, like AIC and BIC,
Yes.
so we can use the degree of freedom to do the calculation.
Yes, this is excellent. It's precisely right. Yes, yeah. So here, remember when we estimate beta of t, we have a reference control on the beta of t, right? So here, although we have j basis coefficients plus the intercept, so we will have j plus 1 parameters, right? But because we have this reference penalty, the effective number of parameters actually is much smaller than 1 plus j. Therefore, to decide the effective number of parameters, we usually using the trace of S. Okay, that's the main reason we're using S here. This is smooth matrix S. Okay. So we can also, because here these parameters is a matrix times y, so therefore the variance of these parameters will be just this matrix times the variance of the y. Variance of y is sigma e square times the identity matrix times this matrix. So we can write down the variance of these parameters in this way. And also, if we assume that the random measurement error epsilon I is RID follows normal distribution with mean 0 and a variance sigma e square, so we can estimate the sigma e square by the sum square error divided by n minus the degree freedom. So here, the degree freedom is we using the trace of the S, the projection matrix, the height matrix S. Okay. So we are also able to calculate the confidence interval for the beta of t by plus or minus 2 times the square root of the pointwise variance on the beta of t. So the pointwise variance of beta of t will be like this. Okay, because beta of t equal to phi t times c, right? Phi t transpose times c. Okay, suppose we have a multivariate functional linear regression, multivariate functions. So suppose we have a scalar, we have some scalar covariance z, and some multiple linear functional covariance x1t to skt. Then we can also using this multivariate functional linear regression model, right? And so we will have actual the slope to the scalar covariance z, and also the functional slope to the functional covariance beta j of t, and we can estimate them using the penalized sum square error by minimizing the penalized sum square error. Okay, so this should be a minus here. Okay, so so here is a summary on this scalar on function linear regression models. So basically now, because we're dealing with the functional covariance, so now we have moved from summation to the integration, right? Okay, so for the integral, it can always understand as a kind of weighted summation, right? Yes, and also we put a smooth penalty on the slope function beta of t to control the smoothness of the coefficient parameters, functional coefficients, and also for the identifiability of the functional linear regression models. To choose the optimal values for the smoothing parameters, we can using the Newman curve out cross validations like we did before, and we can also obtain the confidence interval for beta of t. Yeah, and also this can be generate to multiple or mixed covariates. Okay, any questions?